In this lecture, we describe Hensel Lemma and use it to construct a lot of p-adic expansions. So let us start with the Hensel Lemma statement. So say you have a non-zero polynomial with integer coefficients and you are given a root of the polynomial modulo p. So this a is an integer and this p which you are modulo outing is a prime, and the derivative at our root is non-zero modulo p. So if you are given such a condition, you are given a root modulo p, then you can always find roots modulo p square, modulo p cube, modulo p4 and so on. So we have solutions modulo pn plus 1 for all n. So you have fan is equivalent to 0 modulo pn plus 1. So you have such solutions. Furthermore, these solutions or the series of solutions is related like this. So an plus 1 is equivalent to an modulo pn plus 1. So this index and this index is matching. So in other words, we have the sequence of solutions. So this is our a starting solution, which you say is given as a0, and then you can construct inductively a1, a2 and so on. And each of the element of the sequence is unique modulo pn plus 1. So let us illustrate this construction of a sequence with an example. So example is, so our this f of x is x square plus 1, and we are going to take our prime p as 5. So modulo p is modulo 5. So there are two solutions. You can immediately see 2 and 3 here. So 2 square plus 1 is 5 and 3 square plus 1 is 10, which is again a modulo 5 would be 0. So both 2 and 3 are roots of this equation modulo 5. So now we have to choose a single root to start our sequence. So we will choose 2 to start our sequence. So our sequence is going to be 2 a1 a2, and we are going to find first few terms of it. So now we start using this. So now n is 0. So you have a1 is equivalent to a0. a0 is a, which is now over 2. So 2 and n is 0. So just modulo 5. So this what we have written is a1 is equal to 2 modulo 5, and that essentially means that a1 is actually equal to 2 plus 5t, because modulo 5 this will become a1 is equal to 2. So now we want to find this a1 so that it satisfies this equation. So basically we want to solve this equation. 2 plus 5t square plus 1 is equivalent to 0 modulo 5 square. So actually you can start plugging in numbers and see which one works. There is another easier way to do it by expanding this and cancelling square terms and then working modulo 5, but we are not going to go into detail of that, because this you can just plug it in a computer and find out. So you can see t equals to 1 satisfies this equation. So if you put t equals to 1, this will become 2 plus 5 7. So 7 square, which is 49 plus 1 50. So it is equal to 0. So t equals to 1 satisfies our equation. So a1 now becomes, so I put t as 1 here, so you get 7. Now so this a1 7 is precisely what is satisfying this equation. This we have inductively constructed it so that it satisfies the equation. So now we want to construct a2. So again this a2 will now be equal to a1 modulo 5 square. So notice this index matches this index. So a2 this matches this. a1 we have already solved as 7. So a2 has to be equal to 7 plus 5 square, which is 25t. So again this a2 will satisfy such an equation. In fact, we are trying to find a2. So you plug it in here and you do modulo 5 cube. So 5 cube is 125, and you put this here t as 2. So this will be 57 square plus 1, and if you expand it will become 3250. So in fact t equals to 2 will satisfy such an equation. So again you can expand this and cancel out 5 square and work modulo 5, but you can also plug in numbers to see. So t equals to 2 works nice for us. So therefore you can get a2 here. Now you have this thing you carry right here, and instead of t you put in 2, you get 57. So we have the sequence a0 a1 a2 and so on is 2 7 57. So we can rewrite it in this form. So basically we are just copying this a1 which we wrote here like this. 7 is 2 plus 1 times 5, and then you have this 57, which is again 7, which is this term carried over here, plus 2 times 5 square here. So you can keep on going constructing such a thing, but what we are trying to do is, so when you started with 2 here, this 2 here, our initial term 2 here, we basically have the root of this polynomial modulo 5. So that is x square is equal or equivalent to minus 1 modulo 5. So if you construct such a sequence, we are getting a 5 adic expansion of minus 1, this minus 1 right here. So in fact actually square root of this, because now x will become square root of negative 1. So now consider another example. F of x is x square minus 2. So we are going to solve this equation x square minus 2 equivalent to 0 modulo 7. So essentially when we construct such a sequence in the end, what we are going to get is a 7 adic expansion of square root of 2, because x square will now be equivalent to 2, or x is equal to root 2. So that is what it is going to give us. So let us see this. So you have this equation here. Now you can immediately see plus or minus 3 modulo 7 is the solution. You just pick plus 3. So you just have to start somewhere. So you pick up some number here. So we start our sequence like this: 3, a1, a2. So we want to find a1 and a2. So this is our a0 term, which we are setting as 3. So again for 0, you have again a1 is equivalent to a0, and now you have modulo 7, and this a0 is 3, so you have this term right here, and this you can write it as 3 plus 70. So this is our equation. We want to find a2, so you plug it back into this equation, and you can see t equals to 1 satisfies this. If you actually put t equals to 1, then you get 10 square here, which is 100. 100 minus 2 is 98, and which is 0 modulo 7 square. So this checks out. So now you have found out our a1. So t is 1. Copy this here, put t equals to 1, you get 10. Now again using the same relationship, now you have a2 is equivalent to a1, now modulo 7 square. So this n plus 1 matches this. So this is it. And now you know a1 is already 10. Copy it here. So you have modulo 7 square. So 7 square is 49. So a2 has to be of this form. Again plug this into our equation, which is x square minus 2. Instead of x, we are plugging in a2 because you want this modulo pn plus 1. So now you have cubed here, and t equals to 2 satisfies such an equation. So notice you're working square here, you're working cubed here. And so since t equals to 2 satisfies such an equation, you can plug this in and check it out. So this will become actually 108 square minus 2. So this becomes 11664 minus 2, which is 11662. And the 7 cube is 343, and you can see 343 divides this. So this satisfies the equation. Now plug in t equals to 2 here. So this we are going to copy right here. Plug in t equals to 2, you get a2 as 108. So again you get expansion like this. So this is how it will look like. So you started with 3 here. This is the 3. Then 10 is 1 times 7. Then 108 is just copy this 10. This 10 is 10 right here. This term is copied right here, and then 2 times 7 square is copied here. So you continue going on, and you get a 7 adic expansion of root 2. So most programs actually like Pari or Mathematica will give you p-adic expansions of numbers, because they're just using an algorithm like this to give you expansions. So now we have the super famous example. F of x is 2x plus 1, and we are trying to solve this modulo 3. So essentially we are saying solve this equation. So this is 0 modulo 3. So in fact we are trying to find the expansion of minus half. This is a 3-adic expansion we will find. So because this equation means this thing. So again you plug in 1 here, you know immediately that 1 is the solution. So A is 1. So now we start our sequence. So this A is 1, this is A0. So again here again you will get A1 is equal to A0 modulo 3 because you're taking n as 0. So this is 1 modulo 3, or A1 is 1 plus 3t. Plug in back in this equation, instead of x you write 1 plus 3t. Modulo 3 square t equals to 1 will satisfy this equation. You can see 3 plus 1 is 4, 4 times 2 is 8, 8 plus 1 is 9. So you get our A1. So t equals to 1, this you have copied right here, you get 4. Now again using this condition, you have A2 is equal to 4 plus 9t, because A2 is equal to A1 modulo 3 square and A1 is 4. That you write here, modulo 3 square comes like this. So now again you plug in A2 in this equation here because you want f of A2 is 0. Again you solve it, you get t equals to 1 modulo 3 cube. So again if you put t equals to 1 here and then add 1 to it, this will become 0. So for t equals to 1, 4 plus 9 is 13, 13 times 2 is, this is 26, 26 plus 1 is 27, 3 cube is also 27. So you get 0. So our A2 now becomes, this you have copied right here, becomes 13. So we have this sequence here. So now let us write it down in 3-adic form. So our 4 was 1 plus 1 times 3, which basically we have copied from right here. So t you put as 1. So this is what we have copied here. Similarly, now this 4 you have copied right here, and then you are putting in 9t, so 1 times 3 square. This portion we have copied here. In fact, you keep on going like this. Every time you get this expansion, you keep getting numbers, but our expansion is 1 plus 1 times 3 plus 1 times 3 square and 1 times 3 cube and so on. And as we said before, we are talking about this equation 2x plus 1 equivalent to 0 modulo 3. So we are doing an expansion of minus half. So in the end you get minus half, which is 1 plus 1 times 3, so on. Now this should remind you of a geometric progression. So this is a 3-adic expansion of minus half. This is reminds us of a geometric progression like this. So instead of x we have 3 here, and this is the geometric progression formula where absolute value of x is less than 1. So this is our valuation at infinity. Now these two should agree, make sense, but here 3 seems to be greater than 1, but it is not so if you see the p-adic valuation. So notice that p-adic valuation was p to the negative a, where a was the highest factor of p which divides this x. So if you do 3-adic valuation of 3, this now our x is 3, so the highest factor which divides is just, so this is 3 to the power of minus 1, so a is just 1, so you get 1 by 3, which is less than 1, so p-adic is less than 1, so you can put it here, and this gives you minus half. So you see how our standard geometric progression has carried over right here. So this you can do for all prime numbers, and this is a nice formula which comes up often to show that you are adding these positive terms here, but you're getting a negative number here, precisely because we are using ultrametric valuation, p-adic valuation, rather than the standard absolute value. So we are not using standard absolute value, but p-adic absolute value.